Hello and welcome everyone to JEE Chemistry Tutor. Today we'll start a very important chapter of organic chemistry and one whose importance lies beyond the realms of simple organic reactions. Today we'll start stereochemistry. Now what is stereochemistry? Stereochemistry is nothing but the three-dimensional arrangement of atoms or molecules in space that define chemical reactions. Now when I tell about atoms or molecules in space, that means that we have to consider the three-dimensional arrangement, not a simple plane or a line. Now often I do get asked this question, how is stereochemistry important in the field of synthetic organic chemistry or even druggists and chemists? Now I put forward to you two examples. These are the names of two examples, thalidomide. This is a R isomer and this is a S isomer. We don't need to understand right now what is R and what is S. We'll come to it in due course of time. Now see the simple example. In first view it will seem as these are same compounds. Then why am I saying that this is an R isomer and this is an S isomer? Well, you could see two very important examples. In this case, this thalidomide group is attached to this cyclohexanone moiety through a bond which denotes it is above the plane. While in this case it is attached to a bond which denotes it is below the plane. Now when I use these terms, I should let you know what is above the plane and what is below the plane and what does these bonds signify. So I'll draw them separately. Now this is called the solid wedge bond. And this is called the hashed wedge bond. So this means that this plane or this molecule is above the plane of the system. And this means this is below the plane of the system. Now what do I mean by above the plane and below the plane? Now this is a very difficult example to just visualize. So we see a very simple example. Suppose we have this molecule. This is R prime. We have one above the plane as I said and one below the plane function group. Suppose this is a OH group and this is a cyano group. So what does this mean? So suppose if we take a example to just show, this is the plane of the molecule. So what is this plane? This R and R prime are the plane, which is the straight bonds are the plane. So this R and R prime are in the plane. Suppose the R is here and the R prime is here. So we have one above the plane. See, this OH is above the plane by what I see and this cyano is below the plane. Now suppose this is the OH molecule. So this is above the plane. If this we consider as a plane in which the R and R prime and the single bond is situated, this pen which constitutes the OH molecule is above the plane. And this a cyano group which we constitute as the red pen is below the plane. That means this bond signifies the molecule is above the plane of the system, while this bond signifies that the molecule is below the plane of the system. So whenever you come in stereochemistry, you come through these bonds. This is called the solid wedge bond and this is called the hashed wedge bond. You will always memorize that this is above the plane of the system and this is below the plane of the system. Now if you can't visualize in this way, we will see that this is the plane of the system. Suppose this is the plane of the system, and then what do I mean by above the plane? Because then this is only plane is in vertical system. So we see that this is the plane of the system. Here the R group is there and here the R prime group is there. So above the plane means it is essentially directed towards you. That means the OH, which is, okay, I'll keep this red pen aside for right now. This OH group which is signified by this black pen is towards you. That means if the plane is in the vertical segment, this solid wedge bond indicates that this is going towards you. While the cyano group is essentially behind you. That means away from you. So we can visualize in two aspects that this means this bond is above the plane, or if we consider the plane to be a vertical system, that means it is towards the viewer. And this means it is below the plane or it is away from the viewer. This is very important with regards to stereochemistry, this above the plane, below the plane, because in the whole of stereochemistry, you will come across these concepts of this bond, and this bond. These are very important. So to remember this, what does these two bonds signify? Now we see into this example, which I say is very important because this shows how important stereochemistry is. The only difference between these two examples is that the phthalimide group is attached above the plane to the cyclohexane moiety, which we say that this is in the plane, and in this case this phthalimide group is attached below the plane to the cyclohexane moiety, which is in the plane of the molecule. Also, we can see that this is a sedative while this is a teratogen. Now, suppose we ask a chemist that, okay, prepare me a thalidomide system, which is this, which is used as sedative. And the chemist doesn't understand stereochemistry, suppose. So he gives me this molecule. So he gives me this molecule, this S molecule. And suppose a doctor tries it on his patient and sees that the person, instead of getting sedated, is sleeping, not sleeping at all, if you say. That means this S molecule is not used as a sedative. So by simple tuning of this stereochemistry, this molecule can range from a sedative to a teratogen. That is how important stereochemistry is in natural products and in drug molecules. So these notations are very important. Very, very important in classical organic chemistry or any synthetic organic chemistry. As I say, these have the same names, and both these examples are thalidomide. This one and this one are thalidomides. This is the R isomer. Again, I will come to this later in our videos. This is the S isomer, and the only difference is in these bond connection. If you see, the names of these compounds are the same. This is a chemical name, but if you see the IUPAC naming, it will be a little tougher right now. But it is the same because all the atoms are same. The only difference that you can see from a visual perspective is that this is above the plane while the hydrogen is below the plane. While in this case, this thalidomide group is below the plane and this hydrogen is above the plane. That plays the full significance in changing the complete application of the molecule. Suppose we go to a very simple example. This becomes a very tough example. Suppose we see this and I tell this, okay, this is used as, suppose, some drug. This is not, but I assume that this is used in some drug. And suppose the observer gives me this molecule. What's the difference? They seem absolutely the same. Again, the R and R prime are in plane. As I explained before, this R and R prime, okay, I'll do it in the vertical. I think it's much easy viewed. So here is the R and here is R prime, as I said before. And OH is coming towards you. This is OH. It is attached above the plane in the vertical system. And this cyano, which is noted by this red pen, is coming from behind the viewer. If we again go to horizontal, as I explained before, this OH is coming above the plane where this R and R prime are in the plane. Again, suppose this is the R and here is the R prime, and this OH is coming from above the plane, and this cyano, which is noted by this red pen, is coming from below the plane. So if we just change the configuration and say that the OH is coming below the plane, with this black pen we say that this is coming below the plane, and this red pen, the cyano group, is coming above the plane. The molecule becomes fully different, as I have shown before. So if this molecule is a drug, this can't be used as a drug, or this can be used as a different drug. But these molecules are not the same. Not the same. If someone tells me or if someone tells you that these are same, these are not. That is how stereochemistry is so much important in classical organic chemistry and any organic reactions that will come forward in the future. So what is stereochemistry? Stereochemistry is a three-dimensional arrangement of atoms or molecules in space that truly define the fate of many classes of chemical reactions. Now, before going into the next part, I like to let you know what is the difference, because we say that above the plane, below the plane. But suppose we take this example and we put a mirror here. Sorry, this is a mirror. This is a mirror. So what becomes the mirror? It's the molecule. What does the fate of the molecule after we put the mirror here? This R and R prime will stay in the plane because this is a mirror. Now this OH group, which was attached above, suppose this is R. If you put a mirror here, or if you put a mirror towards you, same thing, this OH will come down because this is a mirror. So if we put a mirror towards you and we put a molecule here, when it goes here, this plane will remain the same because this is a mirror. We are not rotating it. It's a mirror. This OH will go below the plane, So what is the fate of OH? This OH will go below the plane. And this cyano, which was attached below the plane, on putting the mirror here, will go above the plane. If you can see very easily, again, this is the molecule, the cyano was below. We put a mirror here. We go here, the plane remains the same because we are not rotating, it is just a mirror. But this cyano comes above the plane. So in drawing sense, we can see that it comes above the plane. Now if you see, these are fully equivalent, the same molecule. So this is an example of a non-superimposable mirror image. Now I'll come to you why we call it non-superimposable. This is very important and we'll come later when we study enantiomers and diastereomers, which we'll not do today but in subsequent videos. But what is non-superimposable mirror image? Well, you will understand what is mirror image, but why non-superimposable? What does non-superimposable mean? Non-superimposable means that you can't take one molecule and superimpose it on the other molecule. Suppose if we take this molecule, and we want to superimpose this molecule on here, on this molecule. Can we do it? Can we take this molecule from here and just put it on top of it, on top of this? Will it be the same? How? Let us draw in it. This plane will be the same. The only difference lies in this OH and cyano group, which were simultaneously above the plane, below the plane, and correspondingly below the plane and above the plane. Can you superimpose this? Can we take a molecule which is the OH is above the plane and superimpose it on a molecule where the OH is below the plane? We can't do that. We can see that they are mirror images, but can we rotate this by 180 degree and see that we can come here? No, we can't. That means we can't superimpose this A molecule and put it on this B molecule. We can't just take this A molecule and put it on top of the B molecule. They will not be same. They will not be similar, or they will not be equivalent. That's why they are called non-superimposable mirror image. We'll come to this later, but before I go to the next part, we take a simple example of a human system. This is the most easy to understand. You don't have to go to chemistry, you don't have to go to the 3D arrangement because it becomes a little complicated at the start. Suppose we take both hands. We take our right hand, we take our left hand. We know from childhood that these are mirror images. Come on, we keep the right hand, we put it in front of the mirror, it is exactly the same to our left hand. But can we take the right hand and superimpose it on the left hand? Okay, let's try. Can we do it? No, we can't, right? So they are structured different. They are non-superimposable mirror image. We can't superimpose one on the other. This is the classical example of a non-superimposable mirror image. These are called enantiomers. We'll come to it later in our later subsequent videos. But right now, let us see how do we classify isomers and what is exactly stereoisomerism. So isomers are essentially constituted into constitutional isomers, or what we call structural isomers, and stereoisomers. This is our point of interest. Before going into stereoisomers, we see what is constitutional structural isomers. Also, this stereoisomers can be classified in diastereomers, enantiomers. This will come later. You just understand this. First, let us see what is constitutional isomers and what is stereoisomers and what is exactly the difference between them. Well, constitutional isomers are isomers with the same molecular formula but different arrangement of atoms in space. Now, when I talk about different arrangement of atoms, what do I mean? Okay, let us take two examples. Suppose this molecule. We have a methyl here, we have a methyl here, and this one. We have a methyl. We have the same arrangement, we have the same molecular formula. You see here is a CH3, we have a CH here, another CH here, CH2 and an H2, and we have two more CH3 here. So if we write, we have 3 CH3s, 1 CH2, 2 CH, and 1 NH2 group. Now let us come here. Again, we have a CH3 here. If I draw it for clarity, we have a CH3 here, a CH3 here, a CH3 here. We again have 3 CH3. We have 1 CH2. We have 2 CH. And again 1 NH2. So they are the same molecular formula. Nothing is different. So what is the difference? The difference is in the arrangement of atoms. How do I say arrangement of atoms? Okay, let us number first. We know IUPAC numbering. This is the number 1. Okay, numbering, how do we come to numbering? I'll give a little short view. The atom which has the highest atomic number comes first in the numbering. So compared to nitrogen and carbon, nitrogen is of higher atomic number than carbon, so nitrogen will be the first in numbering. And then there are lots of other CIP rules which will come to in later sections. So let us number this first molecule. This is 1, this is 2, 3, 4, 5. So this is essentially a 2,4 dimethyl butylamine, right? So this 2 and 4 position is covered with methyl groups. Let us number here. This is 1, 2, 3, 4, 5. What is the name of this? This is a 2,3 dimethyl butylamine. See the numbering change. It is totally different. So even though the molecular formula is the same, the arrangement of atoms in space is different. Because here the two methyl groups are at 2 position and 4 position, while in this case the methyl groups are at 2 position and 3 position. I will just demarcate it. 3 position. So these are what are called constitutional isomers, or in some other cases these are also called structural isomers, because the structures are different, the arrangement atoms in space. And by what I have described, the IUPAC names are also different. Because of the arrangement atoms in space being different, the IUPAC names will be different. Arrangement atoms in space being different, the physical and chemical properties also will be different because they are not the same. They have the same molecular formula, but the arrangement is different, so the molecule becomes fully different. So you can understand what is constitutional isomers. We have talked about constitutional isomers where the molecular formula is the same, but the arrangement atoms in space is different, like this. See, the arrangement atoms in space is different. We have methyl at the 2 position, methyl at the 4 position. In this case, we have a methyl at the 2 position and a methyl at 3 position. Now, what is stereoisomers then? It is the same molecular formula, but different orientation of groups in space. So let us see the same example just for clarity of constitutional and stereoisomers. So I'll draw the same molecule. Suppose I take the first molecule, this 2,4-dimethyl butylamine, this one. Okay. And we just draw it. Now we include this hash bond. This is solid hash bond, and as I explained before, this means that the methyl groups are above the plane. Again, so if this butylamine is in the plane of the molecule, suppose this butylamine is this, in this plane of the molecule, one methyl group at the 2 position is above. At the same time, this 4 position methyl is also above. Both are above the plane. That means we are considering the 3D orientation of atoms in space. So suppose we consider another molecule like space. I will just remove this name because you have understood what is constitutional isomerism, I think. So I will remove the name and I will put another. So we take another example of another molecule. Suppose methyl. We have amine. We have this methyl which is above the plane, again by solid wedge bond, and another methyl which is below the plane. So we are considering these two molecules right now. We have understood what is constitutional and structural isomerism. Let us understand what is stereoisomerism then, which is the main course of a study. So in this case, the two methyls are above the plane, as I have shown. The two methyls are above the plane in the 2 position, the 4 position. And in this case, one of the methyls is above the plane, while the other methyl is below the plane. So these two molecules are not similar, but they are only different in the 3D orientation of the methyl groups, or the 3D orientation of atoms in space. So these molecules in which only arrangement or the orientation of groups in space and not in the arrangement of atoms are called stereoisomerism. As you can see, they have obviously identical IUPAC names. They will be again 2,4-dimethyl butylamine. This will also be the same. Again, since they only differ in the orientation of atoms in space and the arrangement of atoms is same. Now arrangement, see, this is the arrangement where the methyl are in different position. But when we call about 3D orientation, this is the 3D orientation. That means this above the plane, below the plane is differing. That is the 3D orientation as I've explained before. Since they have different 3D orientation but the IUPAC names the same, or the arrangement of atoms is same, they must have similar physical properties, right? So they have similar physical properties. And they only differ in the 3D arrangement or the 3D orientation of atoms in space. So now we understood what is constitutional isomerism and what is stereoisomerism. Let us do some examples. So I will We have probably understood this. I'll give a 2 to 3 seconds pause for those who can understand. These are very easy. You can do in 1 second. Just do it, and then I'll give the answers of all of them. I'll explain all of them. Also, if you think you need more time, just pause the video here, answer these examples, and then go forward. It is very important that we understand what is constitutional isomerism and stereoisomerism, and then move on to our next part. Okay, let's do one by one. I hope you have all done it. Okay, let's see this. So let's number this. I like the way numbering it is, so it becomes easier. So this is 1, 2. As I said, the atom which has the highest atomic number comes first in the CIP rules. We have oxygen here and carbon here. Oxygen will be 1. Okay, 1, 2, 3, 4, 5, 6. Why am I saying this 2 and why not this 2? Because this is substituted. Again, we'll come to numbering later. These are very important numbering. So I maybe do a video later about numbering, so we'll have a clearer idea. Just now understand that this is the numbering we have. Let's number this 1, 2, 3, 4, 5, 6. The molecule is the same. We have a methyl at the 2 position. We have a methyl at 3 position. Here also we have a methyl at the 2 position, a methyl at 3 position. The molecule is the same. So what is the difference? The arrangement of atoms is same. So these are not structural isomerism. You don't have to think of anything else. You see the orientation of atoms. Let's see the 2 first. The methyl is top, the methyl is top. Same, no difference. But when we go to the 3 position, in this case the methyl is below the plane. As you can see, this is the hashed wedge bond. And in this case, you have methyl above the plane, the solid wedge bond. That's where the difference is. It is at the 3 position where the orientation of atoms is different, but the arrangement of atoms is same in both the cases. So this is an example of a stereoisomerism. I'll just write stereo. You understand that stereoisomerism is like stereo is a stereoisomerism, and we have another is constitutional isomerism. Let's go to the next one. Again, let's number 1, 2, 3, 4, 5. Again, you may say this may be 2. In this case, this molecule is symmetrical. So whatever we consider 2, it is up to us. Somebody may consider this part as 2, and then 3, 4, 5. It's the same. So I'll not confuse it. I'll erase it. Anyway, it is the same molecule since it's a symmetrical molecule. Okay. So this is the numbering. So we have a 5-membered spirocyclopentane where the oxygen is spiro in this case. And suppose in this case we have 1, 2, 3, 4, 5. The molecular formula will be the same. In this case you have 5-membered spiro ring. As soon as you go to this case, we don't have a 5-membered ring. Rather, we have a cyclobutane ring with a OH group attached to it. The arrangement of atoms in space is different. So this is a constitutional isomerism. Again, I'll write in short, constitute. Okay, that means it is a constitutional isomerism. Why? Because the arrangement of atoms in space is different, not the orientation of the groups in space. Okay, I hope you understood this. We go to a very important example, this third one. If you can do this third one, you have understood what is constitutional isomerism and stereoisomerism. Okay, let us see. Let us again number, because I like the numbering part. So this is 1, again with more substituted is the 1, 2, 3, 4. It can be either ways also. Same, it's a similar molecule. Here, so with bromine and methyl, there is a competition between bromine versus a CH3. We know bromine has a higher atomic number, so this should be 1. 2, substituted gets the preference. 3, 4. Now again I say we will come to numbering and naming. Don't get confused with it. It is very simple. Right now you just have to understand what is constitutional isomerism, what is stereoisomerism. I am only giving the numbering and naming because it becomes easier to visualize. We don't need numbering and naming for constitutional and stereoisomerism. We'll come back to numbering and naming, then you will understand why I am using this bromo, why I am saying this substituted one is more preference and all these. We have a rule for this. We'll come to in due course of time. Don't get confused with it right now. Okay, let's see. In this case, we have a methyl group at the 1 position and a bromo group at the same 1 position. Let us get to the second example. We have a bromo group at one position and we have a methyl group at the 2 position. Let us write the names then. 1 bromo, 1 methyl cyclobutane. I'm not writing it full because it doesn't matter. That is this one. What is this one then? This is a 1 bromo. I'm writing the next line. Just for clarity, we can't do that, but just cyclobutane. So this is a 1-bromo 1-methyl cyclobutane. That is, both the bromo and the methyl groups are attached to the 1 position. In this case, the bromo group is attached to the 1 position. In this case, the bromo group is attached to the 1 position. But the methyl group is attached to the 2 position. That means the arrangement of the atoms in space are different. From this and this, the arrangement of the atoms in space is different. We first see the arrangement of the atoms, and if the arrangement of atoms in the space is the same, then we see the orientation of atoms in space. So as soon as the arrangement of atoms in space becomes different, the first condition itself becomes a negative. So we don't need to go to the second condition and verify the second condition. Yeah, constitutional isomerism. Because the arrangement of the atoms in space is different, here the bromo and the methyl are both at the 1 position, while in this case the bromo is at the 1 position but the methyl is at the 2 position. So the arrangement of the atoms in space is different. Again, I'll repeat it one more time. How are we solving this? We first see the arrangement of the atoms in space. If the arrangement of the atoms in space is not same or different, we don't have to go to the second condition. If the first condition negates itself, it is a constitutional isomerism. If the arrangement of the atoms in space is different, then we go to the second condition, where we can see the orientation of the atoms in space. And if the orientation of the atoms in space are different, then only they are stereoisomerism. Okay, the last one. Now it becomes very simple. We again see the arrangement of the atoms. Let us number 1, 2, 3, 4. 1, 2, 3, 4. Both the cases we have a 1 bromo 2 methyl, right? I'm not writing the names anymore. This case also we have 1 bromo 2 methyl. So the arrangement of the atoms in space is same. So it is not a constitutional isomerism or a structural isomerism. Again, what I say before I answer this question is constitutional isomerism is same as the structural isomerism. Is the same as the structural isomerism. This is a very important thing you should remember, because sometimes the examiner confuses you. So just because we are saying that it is constitutional isomerism, you shouldn't forget that this constitutional and structural isomerism is the same. Same case, stereoisomerism and spatial isomerism are the same terms. So don't get confused if the examiner tells you that classify them as structural or spatial, because we have learned constitutional and stereo. You have to remember that constitutional is the same equivalent word as structural. Stereoisomerism is the same equivalent word as spatial. Okay, so let us get into this. As we have said, that the arrangement of the atoms in space is the same in both the cases, this versus this. 1 bromo 2 methyl, 1 bromo 2 methyl. What is the difference? Well, the bromo is below the plane in both the cases. Okay, so you understood by now what is above the plane and below the plane. Okay, so bromo is in both the cases is below the plane. Let us go to the 2 position. In this case, the methyl group is above the plane, while in this case, the methyl group is below the plane. This means above the plane, this means below. So it is the orientation of the atoms in space is different for the methyls, nothing else. The arrangement of the atoms is same. It is the 2 positions where the orientation of the methyls is different in these 2 molecules. So as you know by now, this is an example of a stereoisomerism. I hope you all have understood this. We can do these examples. If you have any problems, do let us know in the comment section. You can contact us in Facebook and Instagram also. The links to that will be provided in the description box. You can also mail us with your questions. Any problem you have in understanding any of this, we will let you know again if you ask us. So do contact us for better understanding of this part of the chemistry. So what we have learned till now. Okay, suppose so you create an algorithm or what we call a tree in it. We have a molecule given to us and the examiner tells us, okay, tell me, is it an isomer or non-isomer? We have the molecule. If they don't have the same molecular formula, they are non-isomers. Tick mark, question is over. Don't have to think of anything else. If they're the same molecular formula, then they are isomers. Okay. Then we go on to the next condition. The first condition negates itself, non-isomer. Question done. 1 mark, got it. But if it is yes, it is an isomer. Then we see the connectivity, as I said. If the arrangement of the connectivity of the atoms in space is not the same, it is a constitutional isomerism. Not the same, constitutional isomerism. If it is the same, then it is a stereoisomer. So whenever we have an isomer, we first see the arrangement of the connectivity of the atoms in space. If the arrangement of the connectivity of atoms in space is different, we close our eyes and say it is constitutional or structural isomerism. Question done. We don't have to think of stereoisomerism. If the arrangement of the connectivity of atoms in space is the same, then it is a stereoisomer. Then we have to go back to further subdivisions. Now this is something I have told in a very brief way. I'll tell later when we talk about diastereomers and enantiomers. If they are non-superimposable mirror images, remember non-superimposable mirror images, two hands. If they are not non-superimposable mirror images, they are diastereomers. But if they are non-superimposable mirror images, they are enantiomers. If you get this tree, you have understood most of stereochemistry. Trust me. Now you can do anything. If someone tells you, this is constitutional isomerism, stereoisomerism, you can do it with eyes closed. If this is diastereoisomers, enantiomers, which will come back again. But if you have understood non-superimposable mirror images, you can do it with your eyes closed. Trust me. Okay, so we have talked about constitutional isomerism. We have talked about stereoisomerism. Now we need to talk about two things. One is configurational isomerism and conformational isomerism. I'll come to conformational isomerism in the next. Configurational isomerism. So what is configurational isomerism? Configurational isomerism are those two molecules which cannot be converted to one another by simple rotation around a single bond. Now, before I go to what is configurational isomerism, let us first understand why this rotation around a single bond is allowed. Now, we know the sigma bond, we can easily rotate around a sigma bond. But if you have a pi bond, the rotation is restricted. This will come back later and I'll explain later how this is important in stereochemistry. Right now, you just understand that around a single bond which consists of a sigma bond, the rotation is allowed, while around a pi bond, which is simply, suppose this molecule, any substitution, rotation is restricted. We can't do simple free rotation around this pi bonds, around this pi bond. This is what you need to know right now. So what is configurational isomerism? Configurational isomerism are those which can be converted to one another by simple rotation around a single bond. Now let us take this example. We have a ketone here and we do hydride ion addition to convert it into a 2-degree alcohol. You don't have to understand the mechanism behind it. We'll come to the mechanism in organic classes. Now just understand why it is happening. Obviously the nature of this hydriding agent controls the stereospecificity. So I have two people in my class, suppose, and this is a hypothetical thing. Suppose Ram gives me this answer and suppose Sham gives me this answer. And I mark Ram correct and Sham wrong. And Sham comes up to me and says, sir, this is the same. These molecules are the same. And I say they are not. And I say prove it they are same. So he says that, okay, this is R and R prime is there. So in the plane we have R and R prime. We have OH either above the plane, below the plane, as I've explained before. Either above the plane or below the plane. And hydrogen the corresponding below the plane, above the plane. But then I say, okay, then you convert this molecule that Ram got to your molecule. In any way possible. And he can't. You can't just simply rotate this molecule and convert it into this molecule. Can you? Let's suppose we have this R, this molecule. We have R here, okay. It's in the plane. So R here, R prime here. We have OH here and we have a hydrogen below. Now we want to rotate it. Let's suppose we rotate it by 180 degree. Okay, so this hydrogen which was below comes above, obviously. And this OH which was above goes below. So this is exactly the same as the second molecule, this one. But as we rotate it, the R which was here goes here. And the R prime which was here goes there. So the R and the R prime also changes its position along with the OH and the H. So upon rotating, you can never get this molecule. As I've explained before also, upon rotating, you can never convert this molecule A to this molecule B. You can never convert this. So these are configurational isomers which can't be interconverted by simple rotation around a single bond. Configurational isomers are also known as molecules which are non-interconvertible. That is, to convert them, you can't just do simple rotation. You have to break a bond. How do you convert this A molecule to B molecule? We can break this OH bond and the H bond, which are above them below the plane, and correspondingly exchange their positions. We can't do by simple rotation. We only have to break the bonds to convert them, and we can't break bonds so easily. So what is configurational isomerism then? As if we summarize, configurational isomers are those which cannot be converted, to one another by simple rotation around a single bond. Okay, what is conformational isomerism? Conformational isomerism are those which can be interconverted by simple rotation around a single bond. So what is conformational isomerism? Which can be interconverted, and they are also called interconvertible systems. Okay, let us see the example which will explain why it is called conformational isomerism. We have a butane here. We have a butane, we have a methyl here, we have a methyl here. Okay, this is the same. All three molecules, all three compounds are drawn here. This one, and this one are the same. Okay, now you want to keep this part of the molecule fixed. So we keep this part of the molecule. Suppose this is the plane. We have a methyl here and another methyl here. So one methyl is here and another methyl is here, and you want to put the red part of the molecule fixed, and you want to rotate only the black part of the molecule. Only the black part of the molecule you want to rotate. So suppose the methyl is in the same orientation. This is the syn orientation. We'll come back to the terminologies I'm doing here. So here the two methyls are in syn orientation. Now suppose I keep this part fixed and rotate this clockwise. So this methyl will come here. This hydrogen will go there. This hydrogen will come at the position of methyl. This gives us this molecule. Now they are interconvertible, right? The same molecule. So we can simply convert one another by rotation around this bond. I'm just rotating clockwise around this bond by keeping this part of the molecule fixed. See, this part of the molecule is the same. It is only this part of the molecule which is converting. And these are the same. And same is the case with this. So these are conformational isomers. This is, as I say, this is a Sawhorse projection. I'll tell you what are projections later, but just for naming I tell, this is Sawhorse projection. So these are same molecules. These are isomers which can be interconverted. This can be converted to this by simple rotation around this bond. And again, this can be converted to this by simple rotation around this bond, this straight bond, or this bond which we are considering here. By simple rotation, we can convert this isomer to this isomer. So these are conformational isomers. Again, to summarize, configurational isomers are those which cannot be interconverted by simple rotation. We have to break a part of the molecule to convert it into other molecule. But conformational isomers are those which can be simply interconverted just by rotation around a single bond. And we don't need to break a part of the molecule to convert it into the other. Okay, let us go to a real life example just to make it much easier. We have this dog and we have this dog. What is the difference then? You see here, the tail we have cut it out and put it in his leg. And this leg we have cut it out and put it in his tail. So we have cut a part of the molecule to convert this dog to this dog. We have not done just simple rotation. So this is a configurational isomer. This is a very bad example, but configurational isomer. Again, humans. Suppose this guy is shouting. He's excited. And this guy is very calm. But we are not breaking any part of the molecule to convert this guy to this guy. These are the same guys. Just that the conformation is different. So this is a conformational isomerism. Suppose if we have a simple example. Suppose I'm sitting like this and I'm changing my conformation. I'm putting one of my hands on the top. So these two are conformations, or we are conformational isomers. When I'm sitting like this and I'm putting one of my hand on top. These two isomers are conformational isomers. Now suppose I'm sitting like this and then I say, okay, I cut off my head and I put on my hand, this hand. And I cut off my hand and put it in my head. Then that two are called configurational isomers. To summarize, configurational isomers are those which cannot be converted by simple rotation. You have to break one part of the molecule to convert it into the other molecule. While conformational isomers are those which can be interconverted by simple rotation around a single bond. You don't need to break any part of the molecule for interconversion. I hope you have got what is configurational and conformational isomerism. Okay, I'll provide you some homework for this. Do this. Classify each as either configurational and conformation. These are very easy. You don't have to do anything tough. This is whatever we have learned. This is from there. Do them. I'll discuss the answers in the next video. And I hope you don't have any problem. If you have any problem with any of this, again, do let us know in the comment section. Also, you can contact us through Facebook, Instagram, or you can directly mail us with your questions. So next day we start from here, and we'll also do geometrical isomerism, optical isomerism, and then we'll go into diastereomers, enantiomers. Thank you.